Hello, my name is Konwoo Song, and I'll be presenting my paper, Neck Goes Ver, Reducing Rotation-Induced Virtual Reality Sickness Through Neck Muscle Vibration. With the prolific use of VR applications, VR sickness has become a key barrier for people to use more VR uses. And while there have been several noted causes behind VR sickness, such as the hardware, such as the display, or gender, age, and VR experience, one main well-accepted model behind the cause of VR sickness is the neural mismatch model, which was originally designed to explain simulator sickness. In the neural mismatch model, it argues that the clashes between the sensory senses, between the visual and the proprioceptive senses, causes the unpleasant effects of VR sickness, such as nausea, dizziness, and disorientation. So to tackle this, I applied different haptic illusion called neck muscle vibration. And muscle vibration is an illusory movement sensation that creates a sense of movement in the muscle even without the physical movement. And when we apply this to the neck, we can feel like our neck is rotating on the right neck locations, even without physically rotating the neck, which causes changes in perceptions and proprioception. So as a system overview, we use the real-time VR rotation information and then use this information to send the target muscle locations and durations in our haptic interface and then vibrate the target muscles, which causes illusion to be perceived, which matches the VR rotation information and hence reducing the sensory mismatch and then decreasing VR sickness. Our contributions are the following. First, a novel wearable haptic interface enabling proprioceptive illusion of rotation sensation using multi-stimulus neck muscle vibration. Second, an exploration to validate the perception change caused by multi-stimulus neck muscle vibration with varying vibration duration and neck rotation related conditions. Third, a formulation of the calibration and haptic rendering process for multi-stimulus neck muscle vibration using real-time VR rotation information. And lastly, an evaluation of neck muscle vibration's effect on rotation-induced VR sickness in a VR scene with varying viewpoint controls. So first, I'll explain how we designed our neck muscle vibration haptic interface and the target muscles that we looked at. In previous works looking at neck muscle vibration, these works would mostly just focus on one muscle, main muscle, and then just focus on the effects of that one muscle. However, in our case, we are looking at a leftward rotation or a rightward rotation on the yaw axis. So we combine two muscles that were used in previous works that looked at the specific rotations, which are the sternocleidomastoid muscles, the SCM muscle in front of your neck, and the splenius capitis muscle on the back of the neck. So for example, if a person wants to feel a leftward neck rotation, we would affect the right SCM muscle and the left SC muscle. And for the opposite one, the vice versa, the opposite muscle counterparts will be vibrated. And we vibrated these muscles using 4 voice coil actuators, which were all driven through a haptic driver, controlled by an MCU, which was connected to our computer, and then hence, which received vibration location information and vibration duration. So using this haptic device, we first started with an exploratory study to see the effects of neck muscle vibration. And we did this exploratory study despite there having neck muscle vibration papers before, because there has been no neck muscle vibration information for shorter and sporadic instances, such as durations of 0.5 seconds or 2 seconds. And these durations are more critical for VR because most of the times when we're rotating our cameras in VR, they are very short, they're sporadic. So we needed a new information on how people perceive these sort of sporadic and short instances. We recruited 9 participants and used the previous works as an example and create a VR scene of a dark room and use laser dots, which is on the bottom one. If you can see, there's a very faint red dot and a blue dot. And the red dot will be attached to the HMD, and follow the people around. And the blue dot was a reference dot, which gave reference of which to look forward, such as 0 degrees, 30 degrees, 60 degrees, and so on. And using this VR scene, we conducted two exploratory studies. First one, we did a study on stationary neck muscle vibration, where we vibrated the neck while people had their neck stationary and looking forward. And second, we implemented neck muscle vibration during neck rotation. So when people will be rotating their neck physically, we will give the vibration during the rotation. So in the first one, we had 8 conditions, with 2 for neck muscle vibration directions, left or right, and also 4 vibration durations. And we measured this by participants self-reporting the rotation sensation by physically rotating their necks after the vibration has completed. And the second part, we had 3 vibration settings, left rotation, right rotation, or no rotations. And we first had the participant train what 60 degrees feel like after showing them the reference points, the blue dot, and having them follow the blue dot with the red dot attached to their H and D. And after they trained what was 60 degrees, moving their neck left and right, we turned off the dots, and then we applied the vibration during the rotation, and observed the ending neck angle, and see how much it changed their perception of or how much they moved. So these are the results of the perception study. So in the left side is the results of the stationary neck muscle vibration, so part 1, and the right side is the results of the neck muscle vibration for the movement. So in the left side, you can see a steady decrease for left neck muscle vibration, and negative is more leftwards, and positive is more rightwards rotation. So as you see, people perceived a more leftward rotation as the duration increased, and a more rightward rotation as the duration increased for the specific left and right neck muscle vibration durations. However, we found one interesting point where some participants would feel this gradual increase and changes. However, they will feel it in the completely different intended location. So for example, when we first explained, we expected a leftward rotation if we vibrated the right neck muscle, right SCM muscle, and then the left SC muscle. However, some people perceived a rightward rotation and an increased rightward rotation as duration increased. And for neck muscle vibration during neck rotation, we saw no big differences, and there were no significant differences between leftward or rightward, or no neck muscle vibrations. So to recap the results of the exploratory study, we first find that the users may feel the opposite illusory rotation from the intended neck muscle vibration, and users exhibit distinctive sensitivities to neck muscle vibration. And lastly, users show no effect to neck muscle vibration if we gave the vibration during the neck rotation. So using these facts, we created a neck muscle vibration profile for each users to calibrate the device and match the sensitivities. For the calibrations, we used a shortened version of the first part of the exploratory study, where people self-reported the rotation perception. And we used 6 combinations of left and right neck muscle vibration, and 0.5 seconds, 1 second, and 1.5 seconds. And using the results of the self-reported angles, we categorize people into either feeling the intended neck muscle vibration direction or the reverse neck muscle vibration direction. And we also divided the sensitivity to low, where people only felt a clear distinction between 0.5 seconds and 1.5 seconds, or high, where people perceive different neck muscle vibration rotation angles depending on 0.5, 1, and 1.5. And using this, we created a rendering process where we use 3 different control models: a video where the people stay still and then so it's 360 video on VR, and a controller where users control the camera angle using a joystick, and then the neck where the people actually physically rotate their neck. And using the real-time information from the VR scenes, in the video, we will use the recorded video rotation angles, and for the controller, we will use the tilt magnitude, and for the neck, we will use the initial neck rotation speed. We divided different duration thresholds depending on the neck muscle vibration profile, and then gave the target neck muscle vibration location and duration to match the rotation sensation with the VR rotation. And using this, now we go to the main part where we see if this is effective in decreasing VR sickness. We recruited 20 new participants with and calibrated the device to them. And we had 6 reverse people and 10 people with low sensitivities who only received 0.5 seconds or 1.5 seconds. And the task of the VR scene was to find a check-in, and we didn't really specify to the participants that we were giving them different vibration styles or conditions to reduce the bias of it. And we just asked the participants to try their best to look around to look for the check-in. And there were 9 conditions, 3 neck muscle vibration settings: the baseline, where there was no vibration; fixed, which was using neck muscle vibration, but we fixed the duration to 1 second; and adaptive, which used our rendering process; and 3 control methods using the video, controller, and the neck. Using this, we used the VR sickness simulator sickness questionnaire to measure VR sickness, and the Slater-Uzel-Steed questionnaire to record presence. And we looked at first the pre-experience SSQ, and we had people experience the VR, and then we measured the post-experience SSQ and then the presence questionnaire, and we gave people a 2-minute to 5-minute break to have them feel better after the VR sickness. So these are the results of the VR evaluation. And as you can see, there has a significant decrease in SSQ scores for adaptive, which is our rendering method using neck muscle vibration, and a significant increase with using neck muscle vibration, which shows that neck muscle vibration reduces VR sickness through reducing sensory mismatch. However, there's one interesting part which shows that for the neck, for both SSQ and presence, fixed, which only gave neck muscle vibration for 1 second, performed better than our adaptive algorithm. So we went back and looked at why this was the case, and we repeated the second evaluation, but this time we increased the rotation speed to match the people's experience, and then increased the durations into 0, 0.5, 1.5, and 1.5 seconds. And through this, we saw that interestingly, at 0.5 seconds, and 0.5 seconds for both cases of left rotation and right rotation, there's a change in perception in neck rotation, which shows that short duration neck muscle vibration is effective for fast and short physical rotations. However, as duration increases, this becomes very less effective. So, for our discussion, we showed that neck muscle vibration rendering with real-time haptic interface successfully reduces VR sickness by reducing sensory mismatch. And however, there's also some neck muscle vibration considerations that should be made, including individual differences, as we've shown through our calibration process, and also neck movement, which shows that depending on the neck speed or the durations, the sensation may vary severely. And also, we saw that there are potential applications of neck muscle vibration outside of VR sickness, as we use here, such as navigation, using its proprioceptive illusions. Some limitations in our work include that all of our works were in the end self-reported measures, and that our VR control methods that we saw separately usually are done all together in an actual practical VR application. So in future works, we are planning on merging these camera controls and to match our neck muscle vibration rendering process to take into account for those camera controls. And also, we are planning on applying different rotations on different axes as well. Thank you, and if you have any questions, I'll be free to answer them.
Thank you very much. Okay, now it's time for the question. So if you have any question, please raise your hand. Thank you. The first one.
Kunwu, this is really cool work. Thanks for sharing. I'm curious, since you talked about the sickness being as a result of the sensory mismatch, right? And here you're focused on one type of movement, right? The neck, like around one axis.
Yeah.
I'm just curious, is there in the literature or evidence, like what are the primary types of movement, translational rotation, and in which parts of the body is causing the greatest sources of sickness? And how did that lead to the focus on this particular one, which is head and rotation around one axis?
So because of the amount of experiments I had, I kind of went really quickly to the related works, but there have also been previous attempts in looking at what causes more sickness in the movements in VR. And while there has been works that looked at eye movements, and how it differs from lateral movements, just moving front and back or left and right, and rotational ones. And they saw that there has been greater eye movements and greater disruptions in eye movements for rotation ones compared to the lateral movements, which cause also more severe, what is it, VR sickness as well. Because, yeah. So because of that, I focus more on the rotation-induced one instead of the lateral ones. And then, yeah, apply neck muscle vibration to those type of, yes,
Thanks.
rotations.
Okay, do you have any quick questions? If not, then we're gonna close up. Thank you very much.
Thank you for your introduction. Good afternoon, everyone. My name is Jaewon Lim from Hanyang University. As many VR researchers know, cybersecurity is still a major barrier for users in virtual world. It appears within minutes as symptoms similar to motion sickness and it break immersion. Even with fast progress in VR and recent focus on the metaverse, the problem is not solved. Because of this, many reports say that about 16 to 80% users feel cybersecurity in immersive VR. Many stop their sessions early. Also, individual sensitivity to cybersecurity varies widely and is shaped by factors like gender, age, susceptibility, and prior experience. So many efforts have been made to reduce cybersecurity. Reducing cybersecurity without compromising immersion remains a difficult challenge. We investigated whether footsteps like vibro-tactile cue provided through a haptic vest can reduce cybersecurity in VR. In many VR use cases, people are sit or standing, so a working sensation is important, and prior studies provide haptic feedback to vestibular system or the feet. However, on the torso, allow the movement and the broader use. Therefore, we provided biotactile feedback that matched the real footstep by alternating right and left step. We also wondered about the effect of adding biotactile feedback when users were already moving, or like when they were working. A few studies find that adding biotactile feedback can reduce cybersecurity, and they explained it as a cognitive distraction. Based on that, we investigate whether adding footstep like haptic cue during real working will also reduce cybersecurity. So we used an omnidirectional treadmill and conducted an additional experiment in dynamic locomotion with synchronized real and virtual movement. We set 3 research questions regarding cybersecurity, presence, and individual difference. Here are our research questions, and here our experimental design. As mentioned previously, we conducted 2 independent experiments. In experiment 1, participants used control-based steering without any physical working. In experiment 2, participants work on omnidirectional treadmill. In both experiments, we compare a no haptic feedback baseline called NF to a biotactile feedback group called VT. We recruit 80 participants in total, 40 for experiment 1 and 40 for experiment 2. 3 participants were excluded due to severe cybersecurity, and we recruited replacement. We conducted both experiments over 2 days, each participant experiencing 1 scene on each day. We measure cybersecurity with the SSQ before and after, and presence using iGroup presence questionnaire. Regarding our haptic feedback, we used bhaptic textures to provide biotactile cue. As shown in the animation, the biotactile feedback was provided alternately to the right and left for forward and backward movement. And sideway movement, biotactile feedback was provided only on the side corresponding to the direction of movement. And all patterns were synchronized to the user speed and directional in rear. In both experiments, participants experienced the same 2 virtual environments. scene 1 was on non-interactive, working around city, and the scene 2 was on interactive FPS on a fixed route, where participants had to defeat a monster with a gun. To prevent any carryover effect, the second scene was scheduled to start at least 24 hours later. Here are our experiment videos. In experiment 1, participants stood in place and used control-based steering. A biprotector feedback was provided according to the direction and the speed of movement. Experiment 2 was the same as in experiment 1, but participants moved by working on an omnidirectional treadmill and turned their waist to change direction. And here are the results. The two experiments are independent, but for readability, we present them together. So SSQ score decreases in both. In experiment 1, the VT group shows a clear reduction, and many participants reported that the Vibrotactile Q felt like working and reduced sensory comfort. In experiment 2, Cybersickness also decreased, but the disorientation was unaffected. In IPQ presence score, in experiment 1 showed a significant increase in presence with vibrotactile feedback because added a virtual working sensation that is otherwise absent in the static condition. In experiment 2, presence was not affected. As the participants were already working, vibrotactile feedback did not appear to provide additional immersion. Regarding virtual environment type, interactivity mattered. In both experiments, the non-interactive city work resulted in significantly higher cybersickness than the interactive scene. Also, no significant results were found in the TNX score and other self-administered questionnaire. For the HR measure during the experiment, only experiment 1 shows significant result for SDNN, IBI, and HR. On the other hand, in experiment 2, only gender and susceptibility significantly affected on cybersickness. Here from the result, we relate the IQ. First, in both experiments, our vibrotactile feedback reduced cybersickness. Also, in experiment 1, presence includes sort of working sensation, and in experiment 2, presence was not effective, likely because participants were already working in the real world. And IQ2, in experiment 1, a working sensation induced by vibrotactile reduced cybersickness by using sensory complete. In experiment 2, cognitive distraction appeared to have reduced cybersickness in a synchronized movement setting. In particular, on the treadmill, thinking in real and virtual movement, lower disorientation, and because of this baseline cybersickness was already low, so the reduction appears small. For IQ3, interactivity in the virtual environment has a large effect on cybersickness. Also, the effect of individual difference on cybersickness differed between experiment 1 and experiment 2, but this part still needs further consideration. So, in experiment 1, which used a static condition, almost participants felt a working sensation from the vibrotactile feedback. In experiment 2, participants perceived the vibrotactile feedback as working sensation, directional guidance, and a strong footstep sensation. And after the experimental report, that it helped to distract them from discomfort. Also, the effect of individual difference on cybersickness differ between the two experiments, which may reflect sample difference, but could also be due to locomotion method or posture. For example, stamina or prior experience may matter. And actually, many participants without gaming experiment felt more comfortable working on the treadmill. Here are the limitations of our study. First, we conducted two independent between subject experiments, which prevented investigation of the interaction between the locomotion method and the haptic feedback. Second, we did not measure cognitive distraction or action directly, and relies on interaction, visual, and the interview, so causal interpretation is limited. Lastly, our sample had limited culture and age diversity. In conclusion, our biotactile feedback that convey a working sensation reduce cybersickness without compromising presence. Also, even when real and virtual movements were synchronized, the biotactile cue shows can reduce cybersickness by cognitive distraction. In future work, we will study long-term VR user experiment using equipment and tasks that can measure cognitive distraction. Here are the reference material. Thank you for your attention.
Thank you very much. Okay, now is the time for the question and answer. So if you have any question, please raise your hand. Okay, I have few questions about. So starting with, so you put this time with three vibrations vibrated, right? How do you decide which position to vibrate as?
Could you please repeat the question?
Okay. Like, so as I saw from the animations, you vibrate like three vibrations in the other best, right? But it can be any kind of position, like right or left only. Then how did you decide this position, or like can it be like only one vibration also can be teach, or like has to be like three or more? This kind of stuff I would like to know.
I think if
I just want to know
I'm not
the
sure
position.
I understand.
Yes, thank you. Mm, mm, mm. I see. Yeah, because maybe next future step, it's gonna be like more complicated like task and stuff, right? Which means if there's like limitation of the vibration, it's really more important to think which part, and so that can be maybe your future work to improve as well. Okay, yeah, that's a good one. And also another question is I think before you doing the experiment, you will tell the participant subject this vibration will means like you have to show the left and right vibration, right? Is it really easy for the user to try
Sure.
to understand like working?
Working?
Is it easy?
Sorry, I'm not sure I understood.
Mm. 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 I see. Okay. Thank you very much. Okay, one more quick question we can take if there is no. Okay. At the back. Thank you.
Thank you for your good presentation. Regarding the vibration intensity setting for both conditions, how did you optimize the model level for the static and dynamic conditions to mitigate cybersickness?
When we measured the motor, we used a process of about 2G in 8.1 and about 2.1 in 8.2. This is the value we found that allows to appear it while minimizing discomfort as much as possible with internal pilot.
Thank you. Okay, so it's time. Thank you for the presenters and questioners. Okay.
Yes, hello. So I'm Philip, and I'm from Wrocław University of Technology. I'm here to present the effects of the unwinding rotations on the VR sickness in a non-simulated immersive telepresence case. This work was done in my former lab called UbiComp in University of Oulu in Finland, with my co-authors Bashak, Evan, Juho, Katrin, Stivo, and Timo. To give you a little bit of background, VR sickness is one of the major drawbacks of using VR headsets. Common symptoms are similar to motion sickness, like nausea, dizziness, and so on. In addition to being unpleasant in a moment, the effects of VR sickness can last for some time after the end of the VR, you're using VR headset, and also VR sickness can degrade the user experience by reducing the feeling of presence and user's task performance. Though there are several theories regarding the cause of VR sickness, one of the most widely discussed theories is the sensory conflict theory. We already heard it 2 times today. So as the user moves in the VR, the eyes see the movement, but our vestibular system does not, so this mismatch between the expected and received sensory information can lead to the VR sickness. So another key aspect of this study is the immersive robotic telepresence, which is basically a way of embodying a physical robot with the use of a head-mounted display. To increase the immersive potential, robot can be equipped with the 360 camera, like in this case. And in this study, we use a 6 degrees of freedom robot, another mobile robot, like was done in the previous studies, for the generalization purpose, allowing the rotation around all 3 axes. Therefore, this study has a particular relevance to environments where such motion in any direction is possible, such as underwater, in the air, and outer space. So we have a 360 camera on the telepresence robot, and we have the user who is observing the remote environment through this camera using the VR headset. Now, how can we reduce the user's sensory mismatch? We know from the previous research that rotational motion is causing more sickness than the translational motion, so how can we tackle that? Let's imagine that we have our camera in the world reference frame. We have references to our camera base and camera initial view, and then when the robot rotates, obviously the camera rotates as well, causing our participant's view to rotate accordingly. We can measure the orientation of the camera base, for example, with IMU relative to the world reference frame, and that allows us to do this, which is to take the inverse of the measured orientation, quaternion or matrix, and multiply the camera view frame by this inverse, creating the unwound camera view frame that is equal in orientation to the original camera view. So you can see the comparison now. We have the same 360 video input, but unmodified view on the left and the unwound view on the right. So you can see that the original view orientation is preserved despite the camera movement. This example obviously doesn't include the user movement, but during the actual study, the movement was encouraged. So our hypotheses were that when exposed to the unwound rotations condition, participant severe sickness will be lower, and at the same time performance in the secondary task will be higher. Why in secondary task? Well, the primary task was intended to be relatively easy, and no difference between the conditions were predicted, more of the sanity check. Moreover, we expected that participants will prefer the unwound condition and will find it more comfortable. So about the study itself. In this study, while sitting on a swivel chair and wearing a VR headset, participants were able to see the remote environment, or precisely a 360 video of the robot traversing the environment. We initially tested it with the real-time video stream, but for consistency reasons, we decided to use the pre-recorded videos. The 360 camera was attached to the 6 degrees of freedom robot arm, and the robot itself was in the room with the few objects like boxes and hanging panels that obstructed the view of some parts of the room. While the robot traversed the predefined path, that included 6 areas that were initially abstracted, participants had 2 inspection-like tasks. The main task, which was the sanity check one, was to check the status of 3 main objects. You can see the example of the main objects on the bottom left. In this case, depending if all the lights are lit or not, participants were asked to mark the object status as correct or not accordingly. And the secondary task was to look for the alien objects inside the environment throughout the whole run. So what are the alien objects? Well, they were literally the alien heads attached to different parts of the environment. So we can see the participants' perspective during the run. You don't see the top left panel, sorry for that. So this is the run using the unwinding rotations on. As we can see, the participants try to look around. They find one of the main objects. When they approach, they mark it correctly. Look around a bit. We don't track the eyes, so we don't know exactly when participants are looking, but we can see the general view. And then they continue to another viewpoint that was initially marked. They see the alien, they mark it correctly. They point at it, yes. And you can see the example of another obstructed area, which is under the table. And this continues for 4 minutes and 40 seconds. So in total, 36 volunteers participated in the study, 40 were women, 20 were men, one chose another, and one preferred not to disclose it. Average age was around 27, ranging from 19 to 41. Each participant undertook 2 4-minute long session with a coupled condition in one and the uncoupled condition in another. Those sessions were scheduled on different days to avoid the potential carryover effect. And because each participant undertook 2 sessions, we prepared 2 variants of the environment with the objective in different locations and randomized the conditions order. Participants for the study were recruited from the university and the greater community and signed up for the study through the online recruitment page. So what we found is that indeed, as expected, participants experienced less sickness in the unwound condition compared to the coupled condition. This was measured with the simulated sickness questionnaire total score. This difference was significant. However, difference in secondary task performance was not significant. Nevertheless, we can still observe the slight positive trend in favor of an unwound rotation condition. One even scored better than I ever did, which is 9 out of 10. And when asked for the preferred session, 78% of participants selected the session with unwound rotation on. Additionally, we asked for the reasoning behind selecting one over another, and we can see that when asked for a reason in favor of unwound rotations, participants often mentioned comfort, less sickness, and that it felt as if the camera moved less. And lastly, participants rated the comfort of the unwound condition significantly higher compared to the coupled condition. This was measured using 7-point Likert scale. So to quickly summarize, we found that the unwinding rotations method decreases VR sickness, increases comfort, and is preferred by users. Therefore, unwinding rotation method shows a great potential to make the tasks requiring high mental workload while moving around remote environments, for example during inspection tasks, more comfortable, with at worst no significant loss to task performance. Thank you for your attention.
Thank you. Okay, now is the time for the questions. So if you have any questions, please raise your hand. Okay, I have a few questions about. So yeah, thank you for the interesting talk. So starting with, so maybe in the future, you are thinking this as more like a robot itself is moving around, right? Like not the stable, like this experiment.
Yes.
So what do you think will happen, or what do you think you have to improve if the vehicle, robot, or robot itself is moving around and also doing the remote control, this kind of situations?
So in this case, we don't. The robot is not actuated by the user, so it is moving around right now on its own. It's predefined path that it follows, and I guess that's the case that you asked for.
Yeah.
But
So
we thought about allowing the user to actuate the robot as well.
yes.
The issue arises that the time of the task completion changes drastically then, and measuring VR sickness with different time duration of such task does not really provide us with the valuable data.
I see.
It will vary depending on the time
Mm.
that user took to complete the task.
I got. Another question is that you also share not only the video but audio, right? Audio information.
Yes. So for this environment, there was not much audio, but yeah, we tested it and we can allow for having some sound effects, for example, with marking and so on, but we did not use it for this study.
So this time experiment is just room environment
Yes,
audio?
yes,
Ah,
without
okay.
any extra sound effects.
I see, I see. Okay, thank you. Okay, one more question we can go with quickly if you have any. Okay, 3, 2, 1. Okay, thank you very much.
Thank you.
Yeah, thank you. So that's actually an CGNA invited article, which is about a lot of work I've done over a few years, mainly together with Bernhard Rieke. And with respect to the time, I just can pitch a lot of the topics. So when you are interested, ask me later or read the article when you don't want to ask me. So without further ado, so where is all of that coming from? So in my PhD thesis, I had a look on something I called DeskVR. It was motivated from neuroscientists working in their specific environment and having a stereoscopic, immersive look on parts of their data. And that's how their working environment is looking like. It's a desk. It has a chair and it's very regular. And the assumption was always they don't want to go into a cave environment or others and just occasionally look into their data. What's happening in immersively, and then they go back into their Excel sheets. So that's what they do, and so that's why I wanted to make use of that environment. And you make you understand that this environment is quite specific because when you because it's one of the things is a lot of users are typically seated. And after my PhD, I had a much more look onto the seated condition and went out of this desktops scenario. And in 2018 already, Oculus Vice President of Content, Jason Rubins, claimed that a significant percentage of Oculus Rift headset owners would rather sit down to enjoy virtual reality rather than take advantage of room scale motion detection. And so that made me thinking, because I think a lot of us, for a lot of us, the model of virtual reality is more something like this, and we have seen examples in this session, or like that.
Typische Grenze nicht zu haben, die du in Virtual Reality sonst immer hast.
And so it was quite interesting to see, yeah, when you provide the hardware to the users, they are much more in favor of consuming VR seated. And so the first question that came into my mind is, do our research findings cover these scenarios or do they generalize to these scenarios? And I want to make this short here. I don't want to talk about that now because I have another half an hour tomorrow for a keynote in the workshop on replication in extended reality, and we will talk about this topic a little bit more there. So I get some more time because the problem is actually it's hard to say because Tim Weisker and I, for instance, had a look on locomotion interfaces, and the reporting often leaves out things like user posture and stuff like that, so you can't really decide if the results are valid or generalized. But for now, let's maybe step back and ask the question instead, why do they sit? Why do people sometimes pick to sit? And I think a simple answer to that is a lot of our living rooms and workspaces don't look like that, unfortunately. And they also don't look like that, maybe also unfortunately. One claim I made is, okay, when we don't have space to actually move around and we have to be stationary and stand, something like that feels much more like waiting in a line. And I think then we prefer to sit down instead. So that's a somehow natural consequence. And the first thing I want to say is, you quickly notice when you think about these things that the counterpart to sitting in extended reality is not really standing. The counterpart is actively moving around. And we will touch on that in a few slides again. But I would say sitting is also not only about laziness. At least, indeed, there are a lot of reasons to sit, and I want just to touch 2 more reasons for it. And there's, for instance, this one. It's in some cases more safe, right? You can fall over dynamic obstacles, and depends on your on the circumstances and the interface design, but it can actually be more accessible when you have a seated scenario. Not necessarily, but I think in general it is. But then, okay, when we accept that for a second, I still ask myself, okay, we accept users are sitting, but what is the whole point about VR then, or extended reality? Because what differentiates it from 3D cinema, right? Which is always the counterexample in lectures I'm giving that's not VR, because it's not interactive, it's not engaging. And that's true, but I would claim again, then when this is important for us, that people are engaged with the experience, we actually have to give them reasons to do so. We have to design interfaces and the scenarios so they want to stand up and walk around or be active by other means, and I will touch on that again in a few slides. And of course we can nudge the user as well. I've brought a little example here from one of our PhD students, Pauline Wimberg. She finished her PhD just recently, and what she, for instance, did, and you can see the blue dots are the walking profile of users under different interaction modalities. And you see when you give users, you can force users with the interaction design, and I don't want to go into detail here, you can force them to move. And what we found, and that's maybe not surprising, is they are then more engaged and also feeling more present in the scene. Nothing really crazy, but you can do that. A work I really always like. Unfortunately, it's only available in German, and this video has nothing to do with it. It's about teleportation. Mantai and Langbane had a look on teleportation and noticed, okay, when we make use of teleportation, users rarely make any use of the walkable space because they then teleport the whole time. And they designed interfaces that encourage users to do both with energy systems and stuff like that. And that's cool, we can do that, but that comes with the risk that I would say is always there, that these things are very individual, and designing paternalistic interfaces in general is a balancing act, right? Some users might be okay with it, especially when it's maybe an exercise environment or stuff like that, but they might be also very fast not happy with that. So, okay, taking that, we can maybe for a second just accept that users sometimes want to sit when being immersed in extended reality. But what are the actual challenges in there? And we touched on one already, but let me highlight, I think, 3 of them. One thing, and that's, I think, why we are here in this session, is cybersickness. While there is research that is showing, when we look into this, into isolation, sitting actually might have some positive effects on sickness. There's some research indicating that. The problem, I would say, is this thing usually comes not isolated, because the problem when we have a stationary user, not only seated, we always have to make use of virtual locomotion and virtual rotation, and we heard about a lot of these things today, and these again induce sickness, and usually the effect is much larger than the gain we might get from people just being seated. So when we don't look at it in isolation, seated conditions or seated scenarios often are more prone to cybersickness. I've done a massive amount of research there, but I don't want to touch on this here further on. Instead, I want to move on to another challenge, and that's the passivity. We talked about that. Virtual reality is engaging. We want people to do something, otherwise it's 3D cinema. And but we already said that somehow it is on us to design interfaces that break this passivity, even if a person is seating. And I've done a massive amount of research in leaning interfaces, which is just one example where you can still have some activity while seating. And leaning interfaces, I would also argue, work the best when seated. So leaning interfaces, for everybody not familiar, are using the human body as a joystick-like interface for locomotion. Yeah, but another problem when users are seated and they are still moving is, and that's a direct consequence of the passive or the more consuming posture that comes with the seated nature, is that their mental model of how they move can drastically vary. And here are just a few examples from a study of ours from 2022, where we asked people what they thought they were moving like, and it was really varying a lot. This is maybe okay in some cases, in others it's not, because it might have direct consequences on distance perception and other things. And so it's important that we provide users with cues that tell them how they are moving. And I brought a very easy sample of an interface a student of mine built, and I think it's a very common metaphor that we see is coming with leaning interfaces, and that's just a hoverboard. That's working, and also it gives a lot of affordances to the user how to use that interface. You might still have problems to understand if you are standing or sitting, it depends, but it tells you a lot how to use the interface and how you are moving. You're not in doubt. So that's an example that's not working all the time, maybe not in professional neuroscience data analysis, but in others. But at the end, and I'm trying to conclude the talk, I think the ultimate goal of interface design, specifically in locomotion, should be to try to design interfaces that are posture agnostic. And I brought a little example that I built. It's a leaning interface that you can use in all different kind of postures. And I have to say, the user using that interface is my wife, and that's a one shot. It was her first try, so bear with her. And it's also not, these interfaces are not made to be used in standing conditions, I would say, because you tend to tip over. I would recommend stepping. But yeah, I'll just give you a look on that. So, and the interesting part about that implementation is that it's just robust against all different kinds of postures, because it's automatically calibrating itself, and the user can change their posture dynamically. You should actually take a step forward. That's easier. Yes, and that concludes my talk. Thank you very much. And I'm happy to take any questions.
If you have any questions, please raise your hands. Okay, I actually have 2 questions. Thank you for the interesting talk here. And first one is, so just now you show us the video, and how do you decide the speed of the movement of this visual part? Because the visual kind is really important, right? So Could you
Yeah.
tell us about
Yeah,
that?
you got the only weakness of that interface, I would say.
Sorry about that.
Because the transfer functions are not the transfer functions are
Mm.
changing, but it's always the same transfer function. But of course, the range you're moving in the different postures is different.
Yeah.
So it's all the same maximum speed, but all the time the same transfer function. So that's definitely a weakness of that interface. So it's changing from the way you're. So when you're really on the ground,
Yes.
you can't. The range of movement is limited, so you will move slower, which might be okay. I don't know, but yeah. There's just a value, a maximum speed, and we are interpolating.
I see.
I think with the power function.
Thank you. Okay. Anyone more?
just ask
Yes,
one?
yes.
Yeah. Regarding the video, but also the previous picture you showed where the person is nicely lying on this reclining chair. Of course, then it's harder to lean because you're already leaning back, so you would work against gravity. So a lot of these posture invariant interfaces go towards, okay, we're using torso as some input modality. But in many instances, especially on your couch, the sofa, the reclining chair, this is not possible. Do you have any thoughts on that, on what are promising avenues to control the virtual camera or the viewport there?
Yeah. So that's actually a motivation for this implementation, because it still works. Even again, the range is limited, and you might want to adapt the transfer function. But as we are usually only tracking the head and not the torso, which is working much better when you can, it still works. So you of course have a limited movement range. You maybe can't go backwards because you're lying, but it still works as it's calibrated. But yeah, you might move very slow when you don't adapt the maximum speed.
Yeah. Hi. A very interesting talk. Thank you. I have two short questions. One is about the let's say sidewalk or kind of a different directions, like we open like a sidewalk, like the crowd. And the other one is about the content generation, considerations for the content generation. If you have any, let's say, suggestions or let's say guidelines in your mind, please let us know.
Okay. I think the first one is the sidewise movements, right? The strafing. I've done that in so different ways over the time, because so usually in a lot of interfaces I try to don't allow any strafing at all, because in my experience it's adding even more sickness. Yeah, the question is, I think, for instance, if you change, if your transfer functions are variant to the movement direction, so because you might be a little bit more limited to the sides, so usually I try to have a elliptic transfer function. Like, that's something that I often did. Yeah, but I've tried a lot of things with this regard, and sidewise movement is interesting, let's say it like that. But when it comes to cybersickness, I often even try to avoid it, because a lot of people really get sick when they move sidewise. And the second question, I'm not sure if I really got it. Other what? Context? Content, okay. Okay. So how to generate content in general, you mean? So no, I don't really have. I'm hoping for AI, really, because that's my hope. So I'm not a content generation. All that assets are bought in the asset store. So yeah, I don't really have recommendation there. It's a major drawback, but I hope this problem will be solved soon.
I've got a question. Do you think that if we could let's say magically detect that someone is approaching to the cybersickness, then we can change something, or this would be very tricky, like could cause even worse reaction?
I think maybe we could. That's actually where my cybersickness research started. I was investigating. So I skipped that part because it's very hard to detect in vitro if somebody is really getting sick. So I skipped that part and assumed I can do that. And we ran a study to, for instance, depending on the sickness level of the user, automatically, for instance, change the field of view or stuff like that. I have mixed feelings about that. The problem is, and we discussed it this morning already, specifically for me, not even if we stack all the existing solutions, it's not helping me. It's maybe delaying the point where I have to step out. And that also was the result of our experiment back then. Everybody got less sick, but later on there was the same level. So I'm not sure if we can. I'm actually not sure if we can revert sickness when it already. I'm not sure. It's just it's. I'm really interested in researching this. We just ran a study where we, together with clinical psychologists, looked on the temporal effects of post-stimulation. Really interesting results, because we were first time able to show that sickness for a lot of people actually is not linearly increasing, but even can immediately appear minutes after the exposure and stuff like that, which really is, yeah, that has severe impacts for instance, carryover effects and how to deal with them.
Thank you very much.
That's gonna be the last question for you. You can just ask it.
Yeah, thank you for the wonderful talk. I have a high-level question. So I always thought of activity or passivity as the responsibility of the application. Like some of the most popular commercial VR applications are Beat Saber, Superhot, etc., which force people to be active, right? So what do you think are the advantages of assigning this responsibility to the interface? There is always cybersickness, but apart from that, do you think there is something more to making interfaces active as opposed to making applications active?
I have to think about that. So my first answer, and that might be not my final answer, is I'm not sure how they differ. So I think Beat Saber is an interface, and it makes you standing, right? When you could play it seated, people would play it seated. But there's something that you have to move around, and that's why people are doing it, I would say.
So the one of the videos that you showed where your wife was, I guess, chasing a bird, that could be done while sitting down, right? You could just do it with a joystick.
Yeah.
But yeah, you experimented with an interface that forced her to be active. So
Yes.
do you think that's part of the application itself? Like, do you think the application is written?
I would say so, yes.
Okay.
Yes, and I would consider the interface part of the application. Of course, you can. We could discuss that, but yeah.
Okay. Yeah. Thanks. Yeah.
Okay, so that's the end of this session. Thank you very much for the presenters.